Thank you. Start. Welcome everyone to this week's WST 20 minutes time domain talk. Today we are delighted to host Dr. Louise Breuval, currently an NISA Fellow at the Space Telescope Science Institute in Baltimore. Louise earned her PhD in 2021 from the Paris Observatory, where she studied the Cepheid distances in the Milky Way using Gaia. She then joined the SHOES team at Johns Hopkins University, working on HST observations of Cepheids in nearby galaxies. And today her research focuses on primarily understanding the systematics of primary distance indicators in the context of the huge debate known as Hubble constant tension. Please join me in welcoming Dr. Louise Breuval. Louise, thank you for being with us today. The floor is yours.
Thank you so much, Julia. Just to check, can you see my slides and can you see the cursor?
Yeah.
Okay,
right.
Perfect. Thank you so much. So since this is a time domain talk, I'm going to talk about variable stars and especially Cepheids. And today I want to highlight the work of an astronomer, Henrietta Leavitt, and her legacy today, the legacy of her discovery. So this is a work that has been published in PASP in 2025 this year. And this is work in collaboration with Caroline Wong from CFA, Harvard, and Adam Rees at STSCI. All right, so maybe you recognize the image in the background here. It's a nearby galaxy. It's the Small Magellanic Cloud, or SMC, but it's not the usual view because this is a photographic plate. So photographic plates are what astronomers used to obtain to measure the sky and to do astronomical measurements 100 years ago. Well, today we have a pretty clear view of the universe, of the nearby environment beyond the Milky Way. We know very well the Magellanic Clouds and roughly distances to nearby galaxies and even to more distant galaxies beyond the local group. However, this was not the case 100 years ago, where even the concept of galaxies was unknown. And astronomers were observing nebulae in the sky, such as the Magellanic Clouds, but at the time they didn't know if they were part of the Milky Way or further away. So the reason why I'm telling you this is because 100 years ago, a team of astronomers were using this telescope located in Peru. And they didn't have CCD cameras, but they were using these photographic plates that they were shipping on boats back to Harvard Observatory in this room, where you can see the man in the background is Edward Pickering, who was supervising kind of a team of women called the Harvard Computers. And they were only women in this team. Back then, women were not allowed to operate the telescopes, and they were even not allowed to publish papers without any male supervisor. But they were in charge of analyzing the data on the photographic plates. So I'd like to talk today about one particular woman in this team of Harvard Computers. I believe it's her in the background. It's Henrietta Leavitt. So she was originally from Cambridge, and she worked as a Harvard computer, where she was terribly underpaid. And unfortunately, most of her lifetime, she was very sick, and she had to work from home or from the hospital, where Edward Pickering was sending her photographic plates to analyze. But she was very devoted, and she loved working on the photographic plates. And she was especially good at measuring variable stars. So back then, we didn't have any software. So to measure photometry or stars' brightness, they had to rely on reference plates, such as this one. So the bright stars were labeled according to their brightness. So you see A and B are particularly bright, and then you go to fainter stars with the following letters. And they had to compare by eye this kind of reference plate with other plates. So these are many, many stars. I believe this is the North Pole sequence. And so basically, Henrietta Leavitt and all the other computer from Harvard had to analyze these plates and compare them between different epochs to see if some of them were variables. This is a notebook of one of the notebook written by Henrietta Leavitt. This one on Magellanic Cloud, small Magellanic Cloud stars. The first column here is the date, so basically the equivalent of MJD. The second column is the plate number. And then each column gives you a different star, and all of them are pulsating stars or Cepheids. And between the plates, you can see light variation. And all these measurements, all these numbers were measured by eye, by comparing to this reference plate I just showed before. So something I was wondering, looking at these notebooks, because I've worked on Cepheids before, I was wondering, have we ever seen the light curves, the plots made by Henrietta Leavitt? And I looked in the notebooks and I couldn't find any. The only light curve that we can find, the earliest, I believe, is this one from Edwin Hubble in 1924. This one was pretty easy because the pulsation period is pretty long, 30 days. So by observing the same Cepheid every night, they could see the variation. But in the previous sample on Leavitt's notebook, the pulsation periods are much shorter. And for example, if the pulsation period is 2 or 3 days, then you're observing it over many, many cycles. And it's not so easy to recover the period. And actually, today, we don't even know how she did without any software or algorithm to measure the pulsation periods. All right, so looking at these notebooks, I started working with Adam Rees and Caroline Wong 2 years ago on reanalyzing this data. So we put all these numbers into a huge spreadsheet, and we try to plot these light curves for the first time and see if they actually look like light curves as we know them today. So that's what we obtained for 3 of them. These are 3 Cepheids. Here with a period of 8 days, 11 days, and 13 days. Of course, there's some scatter, but you can see a typical light curve shape, even with a bump here. So we thought, what if we look at the same objects today with modern telescope? First of all, are they still there? So we recovered their identification number, and we found them in the Hubble catalog, where they have very good light curves. And we have been able to recover the same light curves from the same objects. So the scatter is much better. Of course, this is from a modern telescope with a CCD camera, so it's not a photographic plate. But overall, you see the shape is really the same. There are the same features, like the bump, especially, that you can see on both Leavitt's light curves and the Hubble light curves. The only difference is the amplitude, and it's actually a really good indicator of the wavelength, because the amplitude is a function of wavelength. So because Leavitt's amplitudes are a bit larger than the Hubble V band, it means the photographic plates are bluer than V, and it's actually consistent with what we know of photographic plates. There's comparable to the B band. So it was actually a nice test. All right, so based on these light curves, we wanted to go further and keep reanalyzing the data. There's a question, maybe Richard, feel free to interrupt.
Thanks a lot. I was just wondering, the fits that you're showing there, are those based on templates, or are those direct Fourier series models to Leavitt's data points?
I used a Fourier series. Yeah, but I could have used templates. I believe it's very similar.
Cool. Do you have an idea of the photometric uncertainty of the per epoch measurements by Leavitt?
Oh, I believe by eye it's plus minus 0.2 to 0.5. But looking at the notebooks, yeah, I would say 0.2 to 0.5, roughly. But then looking at the light curves, it's probably 0.2, because we can still recover the light curve shape. So it must be pretty good. All right, thanks. So Henrietta Leavitt picked 25 Cepheids in the small Magellanic Cloud. I do not remember why she picked those 25, but anyway, she represented them on this diagram with log P on the x-axis and magnitude on the y-axis. Magnitude from photographic plates, it's not in a given filter, it's just a provisional scale of magnitude. And here, it's not the typical PL relation that we know today, because today we use the average magnitude, so there's just one line, but here she separated the minimum and the maximum, but it's the same. You see the trend where the brighter variables have the longer periods, and that's the strength of her discovery. There's a tight relationship between period and magnitude, and it's now called the Leavitt law or the period-luminosity relation. So technically, it means that a Cepheid, wherever it is in the universe, if you know the pulsation period, you can measure the distance. Because two Cepheids with the same period have the same intrinsic brightness. So any difference in brightness would be a difference in distance. All right, so what we did was we recovered this data from the original period-luminosity relation, and we plotted them again. So this is the same, but just taking the average between minimum and maximum. And a good indicator of the quality of a period-luminosity relation is the dispersion. And here we have 0.22, which is what we should expect in the optical. So it's already very good and very similar to what we have today. So again, the faint stars have the shorter periods, and the bright regime is here on the right. Something I'd like to show is here, the plates have been digitized by a team at CFA. So this is the equivalent of what Leavitt was measuring. And especially at the fainter regime, it's impressive what she was able to measure, like slight variations in the brightness of this kind of objects. Something else we can look at is the slope of the PL relation. Here, the expected slope should be, the measured slope is shallower and the expected slope should be steeper. So we try to understand why it's like that. The first reason that we believe is responsible is crowding. So these images below are with a modern telescope. With the Warsaw 1.3 meter telescope in Las Campanas from the Hubble survey. And you see that it's not just one Cepheid in the center, but there are many stars in the background that are contaminating the measurement. But Leavitt could not know that. She could not see the contamination. So she was measuring the Cepheid plus the background contamination. So at the fainter, for the fainter Cepheids, she measured Cepheids brighter than they actually are. The second reason is the non-linearity of the photographic plates. So it's a bit tricky, but right now CCDs, when we use CCDs and modern measurements, the response of the CCD is very well understood and calibrated. But for photographic plates, it was not that simple. And at a certain point, when stars become faint, the response of the plate becomes nonlinear and measures the brightness, measure the stars brighter than they actually are. So same effect as crowding. And that, we believe, partially explains why the slope is shallower. All right, so after analyzing this original PL relation, we took the data from the same 25 objects, but this time from the Hubble catalog, and we reproduced this beautiful PL, and the scatter is reduced by a factor of 2, this time with this telescope. And the equivalent of the images are shown here for bright stars and faint stars. Something else that we have improved over time is not just photometric measurements and telescope quality and CCDs, but it's also the understanding of the PL relation. So in the small Magellanic Cloud, just a few words. I removed the slide because I think it's too long, but just so you know, the SMC is very elongated along the line of sight. So now we understand this really well. And instead of picking any Cepheid in the SMC, we now look at the core, which allows us to further reduce the scatter of the PL. All right, so this work has been published. If you're curious to read more, there are some light curve plots and in-depth discussion of this discovery. So this discovery really set set the stage for further and future discoveries, such as the one by Edwin Hubble. But first, so she makes her discovery in 1908 and published the results together with Pickering in 1912. And then Hubble uses this discovery for the first time to measure the distance to the nebulae, and he discovers that they are outside the Milky Way. And then she's nominated for the Nobel Prize in Physics, but unfortunately she had died earlier. However, later, Hubble estimates the first distance to M31 and then eventually proves that the universe is expanding, and all that thanks to the discovery by Leavitt. And now, at the very end of the 20th century, two teams discovered that the universe is not just expanding, but also accelerating. All right, so today, Cepheids are still used as the best understood and the best calibrated tools to measure distances in astronomy. The Cepheids that she used for her discovery are still listed in modern catalogs such as Ogle, Gaia. And something really impressive, I think, is that her identification was correct. So Cepheids can have any pulsation modes or classifications, but what she estimated at the time was already super accurate and really in agreement with what we know today. As I said, modern data reduced the scatter of the PL by a factor of 2. And something fun is that Hubble's law was off by a factor of 7 in the discovery of the expansion of the universe because of confusion between pulsation modes. But in comparison, Leavitt's first PL relation was extremely accurate and really agrees well with modern data. And today, Cepheids are the only realistic way to get a 1% measurement of the Hubble constant, the expansion rate of the universe. So this leads me to a couple more slides, if I still have time, just to briefly give you an overview of how Cepheids are used today. So really the modern update of Leavitt's work. Cepheids are now observed in 3 anchor galaxies, Milky Way, LMC, and GC 4258, where they have known distances or geometric distances. Then on the second rung of the distance ladder, we observe Cepheids again, but in supernovae host galaxies to calibrate the brightness of type 1a supernovae. And then on the third rung, which is the Hubble flow, we observe type 1a supernovae, and by comparing their redshift and brightness, the redshift and distance, we get the Hubble constant. All right, so something that the SHOES team has been working on over the years is a consistent measurement of Cepheids across the first and second rung with only one telescope and one instrument, the HST, which really allows to have a clean measurement without systematic uncertainties due to photometric systems. So everything is in the same system. Okay, so this is the published figure, exactly the same as the previous cartoon plot, but it's the same. You have the first rung with the geometric distances, the second rung with 42 supernovae, which have been doubled in 2022. And on the last rung, the Hubble flow supernovae with high quality data and calibration from the Pantheon team. So in the SHOES measurement, we use near-infrared to minimize the effect of dust. This is what we call a Vezant height index. We fit simultaneously the 3 ranks with 5 free parameters, the Cepheid and supernovae fiducial luminosity, the slope of the PL, gamma, which is the dependence with metallicity, and finally 5 log H naught. And again, all these measurements, at least the first and second rung Cepheids, are all observed with the same telescope, which leads to a Hubble constant of 73 plus minus 1 from the 2022 SHOES release by RIS 2022. So something I just would like to mention today, because I talked about Leavitt's discovery in the SMC, is that in 2024, we have added the SMC as the 4th anchor of the distance ladder. Unfortunately, none of the Cepheids we use today are the same as Leavitt's Leavitt sample. She used Cepheids in the outskirts of the SMC, and we used the core to limit geometry effects. But this is what we obtained with the Hubble Space Telescope, and I think it's really beautiful to see the improvement in the SMC Cepheid PL relation over 1 century. We have no crowding thanks to HST because SMC is very nearby, and we reduced the PL scatter to 0.10 mag and further reduced the uncertainty on the Hubble constant. So now just a few more slides because you might have questions on JWST. Since we observe Cepheids extensively with modern telescope, we have observed them with JWST. Especially on the second run, which was affected by a higher level of crowding with HST. So there's tremendous improvement in the resolution. We can distinguish the background from the actual Cepheid in the images. And this is a PL relation with, in gray, previous HST measurements, and in red, the JWST one. So dispersion is reduced by a factor of 2.5. But most importantly, the distances agree with between HST and JWST. It's not exactly the same filters, but distances are in excellent agreement, which highlights that the crowding is not a bias in the Hubble constant measurement. There's even better, even with JWST, we have identified a perfect host. It's a supernovae host that has a tidal companion here that also hosts Cepheids, but the level of crowding is basically zero. There's no contamination. There's no old population. So measuring these Cepheids give you actually a further 50% reduction in scatter. And today, this is the tightest PL relation outside of the Milky Way, LMC, and SMC local group. So very tight for a supernovae host galaxy at this distance. And you see how clean it looks with no background. And again, this really shows that the crowding is ruled out as a possible source of the Hubble tension. All right, so time for conclusion. The Hubble constant is based on 42 supernovae and 4 anchor galaxies, now all observed with HST. Well, we do have JWST measurements, but so far, now the sample is still too small, so we need more measurements of supernovae host galaxies. But distances agree really well, and crowding is not an issue. Thanks to Henrietta Leavitt, Cepheids are now the most robust standard candles. The systematics are well understood and well modeled. The systematics have been modeled by different teams, and they find very consistent results as empirical measurements. But luckily, there's still a lot to work on, like what is the cause of the Hubble tension, and is there new physics beyond lambda CDM? What is dark matter? What is dark energy? Still a lot of questions to work on, and I'm really glad we have Cepheids as really powerful tools to investigate these questions. And I'm happy to take any questions, and I'll just leave you with this this photograph of the AAS meeting in 1910 at Harvard, where Henrietta Leavitt was present here. So if you want to play a game, you can count how many women were there. But more impressive, if you think that now there are more than 1,000 participants in these meetings. This was really the early stages of the AAS. Anyway, I'm happy to take any questions, and thank you so much for your attention.
Thank you, Louise, for showing us the history of Cepheids in a completely new way, for the summary about H0 measurement, and for giving us some hints about the future. It's time for questions from the audience. Richard.
Thanks very much, Louise. I really enjoyed this presentation. I did want to briefly point out a paper that you skipped in the building on Henrietta Leavitt's work. This is by Einar Hertzsprung from dated May 28th of 1912. So it's the same year that the famous Pickering and Leavitt paper came out, or Leavitt and Pickering paper came out. And in this paper, Hertzsprung used that same relation for the first time for a distance measurement. And he already concluded at that time based on the scale height of the Milky Way disk, that the SMC was external to the Milky Way. So this paper is written in German, so it's not so easily accessible. But actually, I asked my dad to translate it, and I hope to submit this to Astronomische Nachrichten so that it can also be more accessible for posterity.
Oh wow, that's fantastic! Thanks. Thanks for mentioning that. I'm sorry I didn't include it in my slide. I will.
Yeah, it's a bit tricky because it's in German, so not everybody can read it easily. And I quickly had a look at the Hubble 1929 paper. You mentioned that Hubble was off by a factor 7 due to the confusion of populations. I think this is something that is more about the Bade paper, because in Hubble's paper, I looked, I think the main error was that he identified a maximum luminosity to stars, and that did include Cepheids, but it wasn't only based on Cepheids. So it was more the error of saying that all stars have a maximum luminosity, and then that all the other galaxies would scale according to this.
Interesting. I was thinking about the confusion with type 2 or shorter period Cepheids.
Yeah, that's Walter Bade's paper from 1954.
Thank you.
Dante, maybe I see your... Do you have a question?
Yes, thank you, Louise. Very nice. I always learn something. And my question is, how about WST? How can it help?
Oh, that's a good question. So I'm fairly new to WST, but I think future surveys like this should help detect more Cepheids in nearby galaxies. We already have good samples, but having bigger samples would help to investigate things like possible breaks in the PL slope, or at further distances. Well, it's hard to detect them, but in supernovae host galaxies or further away, even in the Hubble flow, detecting more Cepheids in the optical, that would be great, I think, to measure distances to other galaxies that we don't know about.
Okay, great. Thanks.
Thank you. Another question?
Yeah, thank you so much for this wonderful talk. It's always fun listening about Leavitt and the distance luminosity relations. I wanted to ask if there are any more efforts currently for using stuff from the Henry C. Draper Memorial, which basically has all of these measurements in detail, and then re-verifying them using Cepheids or other spectroscopic information for basically improving our measurements of the H0 values. Because
can you just repeat? Excuse me, I didn't get the data you were talking about. Can you just repeat the part?
Yeah. All of the work that Henrietta Leavitt and the other Harvard calculators did was recorded in the Henry C. Draper Memorial, which is currently at Harvard, I believe, which is now being digitized. So is there a plan of basically using that data, which may not have been processed like we do now with light curves, and working with those to basically reanalyze the data that's already there and improve our understanding of the H0 values through Cepheids or other variable stars?
Yes, all right. Thanks for the question. Yes, we are working with a team at Harvard, the people who are digitizing the plates of Henrietta Leavitt, but also other calculators. I do not believe we can use that to improve the Hubble constant measurement, but we can definitely learn a lot about the history of their discovery and a lot of pulsating stars. There's really a lot of work there, and having the plates digitized really help us understand what's behind these measurements. And we actually work on a follow-up of the reanalysis that I presented today with the digitized data to remake the measurements and possibly even find transformations, like empirical transformations between photographic plate measurements and the filters we use today.
Yeah, Yeah, thank you so much. Because I have been following the digitization since I think 2022 now, and there was also a fire sometime, and some plates were lost, I think. But yeah, and also there's this book, I think, The Glass Universe by Deva Sobel, which basically covers all of the history of these wonderful women. And yeah, thank you so much for doing this. This is amazing work.
Thank you so much.
Okay, Lisa, just a curiosity, what is the distance of the spiral galaxy that you showed in one of the last slides?
This one, oh, I don't have it on top of my head. I believe the magnitudes are in this range, so I can check briefly in the paper.
Okay, we can
But it's
check.
among the supernovae host samples, so quite distant for this kind of scatter. It's way more distant than the local group.
Okay, thank you. Other questions from the audience? Okay, I think that we can wrap up the session here. Thank you again, Louise, for the very interesting talk and for joining us today. We hope to see you there next in 2 weeks with the PhD student Teresa Cignano talk. Have a great day, everyone, and goodbye.
Thank you so much.
Bye.
Thank you. Bye-bye.
Bye.
Bye, thanks.
Thank you.